Hello and welcome back to another session of Science 122, Introduction to Physical Science. Last time we talked about the concept of waves, and so let's go ahead and take a look at what we did last time. So in our flashback to last time, we find that we started off with the behavior of waves. Okay, we looked at the idea of reflection and transmission of waves through a material. We looked at refraction and dispersion. Okay, this is the bending of wave as it travels from one medium into another, and how light can spread in terms of different colors. We talked about interference. Okay, in terms of creating standing waves, okay, not only for sound but also for transverse vibrational waves and so on and so forth. We also looked at the idea of resonance, and we looked at several examples of that. And then for the think tank question, we asked the following. When troops march across a bridge, especially a suspension bridge, they are told to break up steps. Okay, the question is why, and explain in detail. And I gave you a little bit of historical perspective in that this came about due to an incident back in 1831 when the troops marching across a bridge in England caused the bridge to collapse. Okay, and so to answer this question, let's go ahead and take a look at our mail response and see if we have a viewer with an answer. Okay, so let's see who wrote in today. All right, today we have a response from Brad of Pearl City. And interestingly enough, he saw an episode of Mythbusters that basically asked this same question. And it has to do with, again, vibrations, and the idea of resonance. The idea was that back in the 1800s, when troops would march across a bridge, they thought that the reason the bridge had collapsed was that they were marching in such a nice, rigid pattern that the pattern matched the natural frequency of the bridge. And in doing so, caused a driven oscillation that increased the amplitude of the bridge and eventually caused it to collapse. Now, of course, how true that is, we don't know. The idea is that, is it possible for you to actually create a situation where a driven oscillation matching the natural frequency of the bridge can actually cause it to collapse? And it has actually happened in the past. In the case of the Tacoma Narrows Bay Bridge in Tacoma, Washington, the bridge was actually caused to collapse by winds blowing on it, matching the natural frequency of the bridge. You can actually see some videos of it probably on YouTube of this particular collapse. In the case of an actual situation where marching across a bridge can cause it to collapse, might be a little bit difficult, might be a little bit different. So in this case, just to be on the safe side, usually troops are asked to break their marching steps so they don't actually do any kind of driven oscillation as they march across the bridge, accidentally matching the frequency of the bridge, causing it to build up in amplitude. Chances are, once the amplitude starts to build up, they would have noticed it and they would have broken step anyway. So to the point where it actually causes the bridge to collapse, that could be a little bit questionable. But that's the idea behind it. All right, so with that, let's go ahead and think about what we're going to be doing today. So far, we've talked about some very interesting subjects concerning physics. We looked at mechanics, for example. We looked at thermodynamics. We looked at electricity and magnetism. And we talked about the properties of waves. What we want to do next is we want to take a look at the subatomic world in terms of looking at the microscopic world of the atom. What is the atom like? So far, we kind of explored this a little bit when we talked about electricity, looking at the fact that the property of electricity resides on the particles that make up the atoms, the building blocks of matter. Now, as it turns out, of course, we now know that that's the building block, but that has not always been the case. So let's take a look at a historical development of how our world, our view of the atom actually came to be. So let's take a look at the overview for today's topics. So for today, we're going to go ahead and get started off with looking at something called classical versus modern physics. And we'll look at some early models of the atom, along with some of the key players in terms of developing these models, including people like Democritus, John Dalton, J.G. Thomson, Ernest Rutherford, and so on. And we're going to move on to some strange puzzles of classical physics that people had difficulty solving, such as the black-body radiation, the emission spectra of light, as well as something called the photoelectric effect. And so with that, it will give us a better feel for what it is that we know and don't know about our physical world in regards to the building blocks, the atoms themselves. So let's go ahead and take a look at where we start off. So let's take a look at, for example, the following. For classical physics, when we look at physics development, physics prior to the 1900s, this was actually an era known as the era of classical physics. Sometimes this is also known as Newtonian physics because Newton played a very, very big part in contributing to our understanding of the way that the mechanical world worked. And prior to the 1900s, after we have studied Newtonian physics, a lot of people consider that we know everything there is to know about how the physical world actually behaves. And so they were pretty good in terms of being able to use the theories developed up to that point to predict what should happen in nature. And the problem, of course, is that this was kind of limited to things that we see on a macroscopic scale. So basically, this dealt with the description and explanation of large-scale observable macroscopic phenomena. when we look at a different situation, when we change now from the macroscopic view to a microscopic view, things look very, very different. Okay, so for example, after the 1900s, something different came about. So let's take a look. So if we look at the development of physics afterwards, okay, we now have something called modern physics. So this is the development of physics since the 1900s, and this is known as modern physics. And what this did was it dealt with the strange behavior of subatomic or submicroscopic phenomena. And we find that it was very, very different from what we expected on a macroscopic scale. When we look at things like bowling balls and airplanes and cars and so on and so forth, they behave very differently, okay, than things that are very, very small on a subatomic level or a submicroscopic level. So let's take a look at a very specific study in modern physics. The study of atomic physics, for example, is a part of modern physics that deals with phenomena relating to the description and behavior of the atom. Now, of course, in understanding the atom, what we're really asking for is an understanding of the nature of matter. What is it that makes up matter? Okay? And so the composition of matter is the question that a lot of people had asked in the past. And probably, one of the first documented discussion of what matter was probably dates back to the early Greeks. So some Greek philosophers, for example, approximately 400 BC, asked the same question: what is the composition of matter? And philosophers such as Plato, Aristotle, and a lot of the other philosophers of the time claimed that matter was continuous. That if you try to take matter and start breaking it apart and tearing it apart, you would have no end to your ability to tear it apart. You can continue to tear and tear and tear, and there will be no end to it. Okay, matter is actually continuous. It flows one into the other. Okay, and so that was a very interesting point of view. Okay, however, although they were in the majority, there were still a few that kind of dissented from this particular point of view. And in particularly, two people by the name of Leucippus and Democritus thought that matter was actually discrete, that there is going to be a finite end to how far you can chop a piece of material up. And for them, Democritus in particular proposed that matter was ultimately made up of these indivisible particles. And of course, these are now known as atoms. So to Democritus, atoms were the tiniest particles that you can divide matter up into. And once you get to the point of the atoms, you can no longer break them into smaller pieces. Okay? And so that was the idea. So you have two conflicting points of view. But, however, due to the greater reputation of Aristotle, the continuous model of matter prevailed for more than 2,000 years before it was discredited by scientific evidence. Okay? And so the idea was that just like his ideas on mechanics, Aristotle can make mistakes due to the fact that he did not perform any kind of experimentation to confirm his suppositions. And so we now know that his continuous representation for matter is not true. So the question is, what is the truth, so to speak? Well, as it turns out, has changed in terms of our view of what the matter is made out of quite a bit. And so to kind of see these changes, let's go ahead and move on to our first topic of discussion. So our first topic today is now going to be the early models of the atom. What was our early view for what atoms look like? Now, one of the first to kind of revive the idea of the atomic model was a scientist by the name of John Dalton. So let's see what he came up with. So in this case, let's take a look at the Dalton model of the atom. John Dalton was an Englishman. He lived around the 1800s, so around early 1800, he revived the idea of the atom to explain chemical reactions. And John was actually a chemist, and he noticed something very interesting. He noticed that when different types of elements come together to form compounds, different material coming together to form new substances, they always combine in a very specific way. That, for example, to make water, you would need 2 parts hydrogen to every 1 part of oxygen to produce a particular amount of water. And that if you try to mix them in different ratios, it doesn't quite work out very well. And so there seems to be this idea that material always tend to mix in these fixed proportions. So the question is why? Because if matter was continuous, you should be able to take any amount and mix them together and it will work out. Kind of like having chunks of clay of different colors. You can take a small piece from one chunk and you should be able to mush them together with no problem if matter was continuous. So the question is, why did this occur in nature? And so he said, well, one way it could occur is because that matter was actually discrete, and that you have this specific discrete way of combining these discrete particles. So let's see what that looks like. So in coming up with his model, he came up with some key points, and he called this a billiard ball model. It's kind of like billiard balls or pool balls. And they were basically indivisible spheres of uniform density, and these atoms made up all matter. And he says also that all the atoms of an element are going to be exactly the same. So you have these identical marbles or billiard balls for the atoms that build up all of these material that represent the same element. And if you have different elements, then what happens is that the atoms of different elements will have different masses. Okay? Now to kind of quickly show you what this might look like is I have some marbles here that can kind of represent his billiard ball model. And instead of using different masses, which is going to be hard to see, I have different colors over here. So the whole idea is that these guys can now come together and combine in very specific ways, for example, in such that if I have one coming together with two, it can then form a compound of a different material where you have a very distinctive ratio of 2 parts to 1 and so on and so forth. So they're kind of getting stuck together in a very specific way. Now, of course, he didn't talk about the mechanisms by which they kind of came together. You can imagine maybe like something that's similar to Velcro, for example. There's certain types of Velcros that stick to others but not to others. And so the idea is that they would have this 1-to-1 or 1-to-2 or 2-to-3 combinations that will always be fixed based on the number of atoms of each type coming together to form some sort of compound. Now we're going to see this in a lot more detail later on when we talk about chemistry. But for now, suffice it to say, this was his idea, used to explain some of his observations in his chemical experiments. All right, so continuing on, we find that in his atoms, that these atoms will combine in definite whole number ratios to form compounds, as we just saw, and that atoms are conserved in reactions. So that if you start off with a certain number of atoms, in your reacting material, then at the end, when you form new products and new substances, you should have the same number of atoms. Atoms are not created nor are they destroyed in chemical reactions. And we still hold that to be true today, for the field of chemistry. And so his model is very simplistic, so it might look something like this. So for his model, all it was is a solid billiard ball. This was proposed at the early part of the 1800s. And then, a little bit later on, we have this new discovery, and this discovery came from an English physicist by the name of J.J. Thomson, nearing the end of the 1800s. Now notice about 90 years has gone by now. Basically, J.J. Thomson was able to identify the greenish beam in a cathode ray tube as being composed of negatively charged particles. What J.J. Thomson was working on was actually working with electricity. And he was actually looking at something that might have looked like this. So this is a glass tube, and what it does is that it is something that has two pieces of metal that are embedded in it. So here's one piece here that's in there. And the interior of the tube is evacuated, so you take out as much of the air as possible. And what you would do is you hook up a battery to the two ends right here, the two the cathode, the two electrodes. And when that happened, he would notice a green beam traveling from one end to the other. And so he noticed something very interesting, that whenever he energized a cathode ray tube like this, that a green beam would emanate from one of the metal cathodes, metal electrodes to the other metal electrode. And so he wanted to figure out what those things were. And he noticed right away that they reacted to a magnetic field. When he brought a magnet near it, it started to bend. So you knew it wasn't just a beam of green light. It had to be some charged particle. And from experimentation, he noticed that it was negatively charged. What he did was he had actually discovered the electron. So let's see what that led to in terms of discovery. So he had just discovered the electron. And he was able to determine that the charge to mass ratio of these electrons using a method developed by the American physicist Robert Millikan. And so what he did was he also said that, well, what if, in finding the charge to mass ratio, he found that it was the same regardless of the metal that was used for the electrodes or the gas that is in the tube. So at first he thought, well, maybe the green beam actually was a specific material coming from a specific combination of metals inside the cathode ray tube. So what if I were to change out the metal? What would happen? So that's what he did. He looked at different combinations during experimentation, but regardless of what kind of metal he used for the electrodes, he always had the same green beam. Then he thought, well, maybe it's because of the residual gas that is sitting in there. There might be some air in there, and that might be what's giving the green beam. So he would replace the air inside, pump out as much as possible with other kinds of gas like argon, neon, and so on and so forth. And when he did that, he noticed that the green beam still emanated. So it doesn't matter what he used, it's always the same green beam. So that led to only one possible conclusion. So basically, that's meant that the atoms of all types contain these electrons. They were all able to give this particular green material. And so in 1903, he proposed a brand new model for the atom. He called this his plum pudding model of the atom. And this is what it would look like. So for J.J. Thomson, imagine that you have a spherical cloud of positive charge there, and then distributed throughout as if it were raisins in the plum pudding, you have the electron. Now for us, of course, being Americans, we probably don't really know what a plum pudding is. So another way of looking at this model is to think of it as a blueberry muffin model. Okay? So the idea is that the muffin itself is a uniform distribution of positive charge. Now, he realized that it had to be positive charge because the atom itself is going to be electrically neutral. So if the electrons were negatively charged, there must be some positive charge that is still sitting in the residual of the atom itself. Okay? And so he noticed that that must be the rest of the atom. And so this idea of that pudding in there being positive, and then the raisin that goes into the pudding as being negative, or in our case, okay, the muffin being positive, okay, the blueberries being negative. So a very simplistic type of material view that has a very uniform, okay, look to it. Okay. Now, of course, once you have this model, one thing that you might want to do is say, well, let's test it out to see if this particular model holds any validity. And so basically one of his students, okay, Ernest Rutherford, for example, decided to test it. Okay? And so Ernest Rutherford was working out of New Zealand at the early part of the 1900s, about 1911. And he basically performed an experiment in which alpha particles were used to bombard a thin film of gold foil to see what would happen. Now, what is the premise behind this particular experiment? Well, think about it the following. Let's say you want to probe something. Okay, let's imagine you walk into a room and you see up in the corner of the room a big black cloud hanging over. Okay, and you're wondering, gee, I wonder what's in that cloud. Well, how are you going to figure it out? How are you going to test that cloud to see what's in there? Well, you probably don't want to stick your hand in there. It could be a monster in there, bite your hand off. So you probably don't want to do that. So what do? Well, you probably want to go outside, grab a whole bunch of rocks, come back in, and start throwing rocks at it. Okay? So as you throw rocks into that big black cloud, if you hear it go right through and boom, hit the wall behind and keep falling off, then chances are if you do that 10 times and every time it goes right through and hits the wall, chances are there's not much inside that cloud, nothing much solid anyway. On the other hand, if you threw something in there and you hear donk and you see the rock come flying back at you, well, chances are, well, it hit something solid in there, there's something inside. Okay? So in this sense, you have kind of basically using a indirect method, kind of figure out that there is something solid inside the cloud. So in the same way, Rutherford wants to see, well, what would happen if you take an atom, okay, that's large enough, and you start shooting subatomic bullets at it, okay? And as the bullet hit the atom, how would it interact? Well, he had a certain idea as to how it would interact if the atom was indeed like J.J. Thomson's model, like the plum pudding. Most of the time we would think it would just go right through. Imagine a big Nerf ball that had tiny little BBs embedded in it. Okay? If you have a high-power rifle and you want to shoot at it, okay, chances are that rifle is going to tear right through it. So even if you hit with the BB would be so insignificant it wouldn't deter or change the path of the bullet very much. So he would expect to kind of shoot right through atoms very easily, okay, based on the plum pudding model. So he actually did that. Okay? Now the reason why he chose gold is because of the fact that gold has very large atoms. Okay? Gold is a pretty large atom. And also, gold has the unique property of being able to be rolled out into very, very thin sheets. Okay? We find that it is going to be a common property for a lot of different kinds of metals. But it's going to be very, very thin. So that means you only have a few atoms of gold that you have to penetrate when you shoot at it. Okay? And so that made it easier. Okay? Otherwise, if you have a very thick piece of material, if you shoot it, it doesn't come out, you don't know anything about it, basically. And so he created an experiment that looks something like this. Okay? And so first of all, he needed some sort of subatomic bullet. And at that time, as it turns out, radiation had been discovered, and a particular kind of radiation called alpha particle was particularly interesting to him. And so he basically procured a sample of this material that will emit alpha radiations. We now know that alpha particle is nothing more than a very heavy, not very heavy, but a helium atom that has its electrons stripped away. Okay? And so he would shoot these subatomic, atomic bullets at a large gold atom and see what would happen. And so you can imagine a box here that was lead lined with a little hole, punch in at the end, and so the material that would emit the alpha particle would be shooting inside, and only alpha particle that came along this line would come out that would create a beam of alpha particles. And somewhere down the line, we put a sheet of gold foil as a target, and then we would wrap a screen around it to detect what happens to the alpha particle as it hits the gold foil. And this was a fluorescent screen, so when the alpha particle hit it, it would give off a flash of light. And this whole thing was done in a dark room. Okay? Now, of course, Rutherford now, he was a pretty prominent scientist by now, so he didn't actually have to do this himself. He had two of his assistants, a postdoctorate and also a grad student, actually sitting in this dark room counting out flashes on the screen to see what happened during this experiment. And they actually had to sit in the dark room for 2 hours to get their eyes adjusted before they can even start taking data of these flashes. And so what happened was, as he shot the alpha particles out, it would hit the gold foil, and he would record the results. And most of the time, he saw something like this. Once in a while, however, he saw that the alpha particle would get deflected a little bit off to the side like this. And then finally, once in a great while, he would see results that look like this. So let's go ahead and go over these three results and see what it meant. First of all, when he performed, the vast majority of the alpha particles passed right through the foil. And this is exactly what he had expected. He expected the alpha particle to pass right through, if the model was correct, that plum pudding model. And even when it did not, even when a few of the alpha particles were deflected by a small amount, that could still be explained. So if the alpha particle came in, hit some of the electrons, hit several of the electrons successively, and then it might get deflected just a little bit. So in this case, even a little bit of deflection can be accounted for through successive collisions with the negatively charged electrons. But the last result, a very small number, 1 out of about 20,000, actually bounced backwards at very high angles in the back. Well, that was totally unexpected. And as it turns out, it was not a fluke. They were able to actually see it over and over again, albeit a very small number, 1 out of 20,000 roughly. But they did enough observation that they saw that it was statistically important. Well, this is such a weird result that Rutherford was quoted as saying, it was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it came back and hit you. He was that blown back by it, so to speak. He just couldn't believe what had just happened, because this is something that was totally unpredictable by Thomson's model of the atom. The plum pudding model just does not have the necessary components to kind of explain what's going on here. So Rutherford said, well, that means that something is still not quite complete about the atomic model. Something is not right. So he came up with his own ideas as to what is really happening. And to explain his result, basically, he had to come up with his own idea. And so he concluded that the atom must have its positive charge and concentrated in a tiny massive core, which he now called the nucleus. So rather than having the positive charges spread out uniformly throughout the volume of the atom, he said, no. All of that must be concentrated now at a very, very dense center, at the center. And it is because of this that now, as the alpha particle came in, if it were to hit that center head on, that nucleus head on, that's what would cause it to bounce backwards. It would be kind of like shooting a BB gun at a bowling ball. If you miss the bowling ball together, no problem, it will go right through. If you clip the edge of it, that will be deflected for over a small amount. But if you hit it near center, it would then bounce back at you. And so that's the idea behind what's going on. Now, of course, inside the atom, the nucleus are far enough apart. Most of the time, you're going to miss it. But once in a while, you do hit it straight on. All right, so in this case, from calculations, he estimated that the electrons of an atom moves around the nucleus at a distance of about 100,000 times the radius of the nucleus. And that's actually a pretty good number. So basically, what you find is that his model will look something like this now. You have the nucleus in the middle, and you have these electrons that are now going to be buzzing around it on the outside. This is now called the nuclear model. The focus is now on the nucleus. And of course, he did further experiments to kind of test to see what the nucleus was really like. And his experimental results came back such that, in 1918, he identified the discrete unit of positive charge in the nucleus, and is now known as the proton. So that makes it the second component of the atom. The third component, the last component of the atom, in this case the atomic nucleus, the neutron, was not discovered until 1932 by James Chadwick. Now you might want to think about why it took so long for them to actually discover the neutron. Once the electron was discovered, it didn't take that long for the proton to be discovered, but it took quite a while for the neutron to be discovered. The question is how come? Think about that. All right, so with that, we can now look at the nuclear model in terms of the components of an atom, and this is what it would look like. So for the different particles, the charge, the mass, and the size, here are the comparison between the electron, the proton, and the neutron. Notice that they have charges that are relatively small, using the unit of coulombs. Electron and proton have exactly the same charge. The only difference, of course, is the electron will have a negative sign attached to its charge. So forget the negative sign there. The mass is also extremely small. So it turns out the electron is about 1,800 times smaller in mass than the proton or the neutron. Notice the proton and neutron are pretty close in mass, the neutron being a little bit more massive. And then look at the sizes. The sizes are very, very small. 10 to the minus 18 meters for electron, 10 to the minus 15 for proton and neutron. So in other words, the electron is about 1,000 times smaller than the proton. 1,000 times smaller than the proton. So you might say, well, how does that compare? Well, I'll give you a visualization. If you can imagine the electron to be about a centimeter in size, about the size of a pea here in your hand, the proton sitting next to it, or the neutron sitting next to it, would be about the size of a 4-story building. Okay, 4-story. It would be 10 meters tall. Okay, that's how big the discrepancy is in terms of size. Okay, so keep that in mind. Furthermore, if you look at now the structure of an atom, basically at 99.97% of the mass of an atom is located in the nucleus. So most of the mass is stuck there right in the center with very little mass, buzzing around on the outside in the form of electrons. And more importantly, if you look at the size of an atom, the diameter of an atom is on the order of 10 to the minus 10, or 10 million atoms will be needed to form a 1 millimeter chain. So these atoms are extremely small, okay, very small. But still, when you compare the size of the atom to the size of the neutron or proton, there's a big gap. Okay, 10 to the minus 10, 10 to the minus 15. That is going to be 100,000 times smaller. So the proton is 100,000 times smaller than the atom itself. But what does that mean then? Well, imagine now if you have a proton and you have an electron and you want to make an atom. And the simplest of all the atoms is going to be the hydrogen atom. And what it is, it's going to be one proton, one electron, and the electron is going to be buzzing around the proton somehow. Well, in this case, okay, what would it look like? Well, imagine the proton to be about this big, about the size of a postage stamp tooth, so about 1 millimeter in size, about the size of a pinhead. Okay, then what you need to do is you need to go about 2 football fields away before you will locate the electron that goes with this to make up the hydrogen atom. And of course, that electron will be about the size of a dust speck. Okay, so what's all that in between? Well, it's just nothing. It's empty space. So what you find is that for hydrogen atom, with that one proton, one electron, right from all this relative size, you find that it is mostly just empty space. Okay, and as a matter of fact, an atom is roughly 99.999% empty space. So we're really mostly empty space. Okay, so all the mass is kind of stuck in the middle, and then all that space between the nucleus and the electron. The atom itself is just mostly empty space. Okay, so when people call you airhead, don't take offense. It's true. Okay, we're mostly just empty space. Okay, but think about the consequence of that. Okay, a little bit later. All right, so now that we have the nuclear model, let's go ahead and take a look at the atomic in terms of how does an atom stay together. Well, first of all, remember we talked about the idea of electrical forces. Okay, so for example, we have 2 electrons, they'll tend to repel each other, as we know from before. If we bring the proton along with an electron together, they tend to attract each other. So again, like charges repel, unlike charges attract. If we try to get them close together, you'll find that if I try to put 2 electrons really close together, they will repel with a stronger force. Remember, this is Coulomb's law, the inverse square for the distance. So as you decrease the distance, the force increases as 1 over the distance squared. So be careful with that. If I bring the 2 opposite charges together, then the attractive force also increases dramatically. And so if that's the case, what happens inside the nucleus of the atom? Well, in this case, we have to look at the following. If I try to put 2 protons near each other, they would tend to repel each other due to electrical repulsion. If I try to stack them on top of each other, bring them really, really close together, well, that electrical repulsion is going to be very, very strong. So in other words, if we try to build an atom by putting protons inside the nucleus, well, guess what? There's a natural tendency for them to push away from each other. That's going to be a problem. So how do we overcome that? Well, as it turns out, nature has a way of overcoming that. So far in what we've talked about before, we've talked about 2 different fundamental forces of nature. We talked about the gravitational force, which is a force of interaction between masses. We talked about the electrical force, electromagnetic force. This is the force between electrical charges. We now are going to introduce a 3rd type of fundamental force. We call this the nuclear strong force. And this force is going to be the force of interaction between particles that sit inside a nucleus of an atom. This is called the nucleons. So this is the force of interaction between nucleons. So what it means is that any 2 particles that sits close enough for them to be inside a nucleus of an atom, they will actually attract each other with this nuclear strong force. It doesn't matter about the mass, it doesn't matter about the charge, they just basically attract each other due to their proximity in the nucleus. And this might look like this. So in this case, we might imagine a nuclear strong force pushing the 2 protons together. Now, in generality, if you had just 1 proton, 2 protons together like this, the electrical repulsion is going to win out, and it's going to basically break it up. The nuclear strong force is not going to be strong enough to hold the 2 protons together. And so what we need is help for the protons. And so that's how we can actually have a stable nucleus for an atom. We need to bring in that 3rd particle that we talked about, the neutron. And so the neutrons serve a very important role. So let's see what it does. So in bringing in the neutron, what we can see is that for a neutron and a proton together, they do not have any electrical repulsion. So all they will feel is the nuclear strong attraction. Same thing if I had two neutrons, for example. They do not feel any electrical repulsion, but they still will see the nuclear strong attraction. So what that does is that if I were to try to create an atom that looks like this with two protons and two neutrons in the nucleus, the protons will have a tendency to try to push away from each other due to electrical repulsion, but they will also see nuclear strong force attraction, not quite enough to overcome the repulsion. So what we do? Well, we look at the other interactions. We now have these two neutrons pooling together. Those pooling together, neutron-proton, proton-neutron, neutron-proton, proton-neutron. So each pair of the nucleons will have this nuclear interaction causing it to basically pool together. And together, all of these combined forces of the nuclear strong force will now hold the nucleus against the repulsion of the two protons outwards. So this gives you now a stable environment. So basically the neutrons serve as glue that holds the nucleus together. Now we find that as the nucleus gets bigger and bigger, the ability of each of the neutrons to hold them together becomes weaker and weaker. And that will lead to eventually what we call nuclear decay. And that's going to be a totally different topic altogether. Okay? All right, so that's the stability. So the neutrons are very important in keeping the atoms together in terms of the nucleus of the atom intact. The problem is, of course, even with this new model, the nuclear model, there are still certain things that we don't quite understand regarding the behavior of the atom. And this is really highlighted at the turn of the century when basically scientists, especially in the field of physics, came across some very intriguing problems that they could not solve, that did not have the answer to. And these problems led to a brand new way of thinking and allow us to basically revise our view of the atom in a very dramatic way. And so to kind of see this, let's take a look at what some of these problems are. So let's move on to now our next topic of discussion, which is now going to be black body radiation. In black body radiation, what this is a classical problem that looks at what happens when an object gives off radiation due to its temperature. And in the ideal situation, when I have an object that is totally black, it would then be an ideal radiator. It would be ideal in terms of its ability to give off radiation. So we learned that color is very important in determining the amount of radiation or the rate at which radiation is given off by an object at a certain temperature. Black bodies are especially efficient. They're the perfect emitters of radiation. So let's see what this looks like in terms of the problem. So in the case of the black body radiation problem, this is a problem with classical prediction as to the way that solids would radiate energy. So as you heat up an object, how does it give up energy? Well, an ideal black body absorbs all incident electromagnetic radiation, but it will also emit radiant energy to remain in equilibrium. So if you have an object that is black, for example, when you shine light on it or any kind of energy, electromagnetic energy that falls on it, it will absorb it. But at the same time, it has to give energy back off in the form of radiation to maintain equilibrium to stay at a given temperature. So the question is, how does it give off this radiation? Well, what you find is this. As the temperature of a solid increases, as we heat up an object, it will radiate in such a way that radiation emission will also increases at all wavelengths. That means it will give off more and more different energies of radiation. So all the different wavelengths, different energies of radiation will be given off. More of it will be coming out. Furthermore, you'll find that the component of maximum intensity will shift to a lower wavelength or higher frequency, higher energy range. Now, just the words themselves will be kind of confusing. So let's go ahead and try to visualize what this means. So let's take a look at the following graph. So here in terms of thermal radiation, if I draw a graph where the intensity of how bright the radiation is along the vertical, and the frequency, how quickly it oscillates, how many cycles per second along the horizontal, that horizontal line, the frequency is really comparable to energy. The higher the frequency, the higher the energy. So if we were to heat up something, we'll see that it will actually give off energy like this. It will be at a certain temperature, and notice that it will peak at a certain value. So you notice that there's a range of frequency that is being given up. So in other words, it's giving off different colors and different regions. So if this is in a visible region, it will be giving off colors that are uniformly throughout. But it will peak at a certain value. So that means the maximum amount of emission is going to be at a certain value. So for example, when you turn on your electric stove at a temperature of about 450 degrees, it will kind of glow orange, for example. But if you increase the temperature, what happens? Well, when you increase the temperature, all of the wavelengths also, in terms of the amount of emission, increases along with it. So let's see what that looks like. So at this second temperature, you see something that looks like this. Notice in this case, there's now a broader range of frequencies that are being given off, and you are now pushing more towards the high frequency end. And the peak also occurs at a higher frequency. So you're giving off now energy at a higher frequency, higher energy level. Well, that's kind of like when you look at a temperature of a tungsten filament in a incandescent light bulb. Okay, that's now burning at about 1,000 degrees. In that case, it is now giving off energy that's shifted all more over so that you have more blues and so on and so forth. Now it's kind of like a white-like color, a combination of colors that are all uniformly spread out. So the idea is that there's a shifting of energies to higher and higher frequencies, higher energies as the temperature increases. If I do this one more time with a third energy, it might look something like this, third temperature. So as temperature gets higher and higher, the range of frequencies becomes greater and greater, and the peak, the maximum frequency, shifts over to the higher value. That's what we see experimentally when we actually heat things up and we measure the amount of energy given off, the radiation given off. However, this is not what was predicted classically. If we were to look at the math that would describe what's happening, notice that the three temperatures, each one bigger than the other. If you look at the math, we find that according to classical wave theory, the intensity of the radiation should be proportional to the square of the frequency. What does that mean? Well, it looks something like this in terms of, the idea is that as you get higher and higher temperature, basically you should peak out so it looks like a parabola, half of a parabola. It's a quadratic function, basically. It's a square function. And mathematically, that's what was predicted. However, this was not what was observed in the lab. So this is not what is actually observed, and this discrepancy was known as the ultraviolet catastrophe. And there's a very good reason why this is called the ultraviolet catastrophe, as we will see. So let's take a look at what this means. So if you look at the emission graph, intensity versus frequency, this is what is predicted classically. So if you do all the math, and you look at all of the results from classical understanding of how black bodies would give off energy, this is what you expect. You expect to see this graph that goes up as a square of the function for the frequency. The problem is, in reality, we see this. This is the actual experimental observation. So notice that there's a very, very good match at the low frequency end. That the low frequency end, the two matches very nicely together. They coincide right along to each other like this. It is only when you get to the higher frequency at around the ultraviolet region where classical prediction goes up while the experiment goes down. There's that split right at the ultraviolet region. And that's why this was called the ultraviolet catastrophe. The disaster occurred at that particular region where our experiment no longer matched with our theory. So we have no predictability as to what's happening out there. We had no understanding as to why. And for the longest time, this was a puzzle for people. They couldn't understand why. So there was no physical reason why that anyone can come up with at the time that would explain what's going on. It was very important to study this blackbody radiation because really what it does is it shows how atoms of any material in the solid state emit and absorb radiation. So the reason why we want to kind of understand this is because we need to know what is the atom doing inside of the material. How is that atom going to be absorbing the radiation that's being given to it, and how is it going to be releasing it back to the environment? If we understand the mechanism that is involved, then we can understand what the atom is doing, and then from that we can understand what the atom really looks like in terms of its mechanisms, in terms of its makeup, and so on and so forth. So that's why this is important. Also, classical physics was unable to correctly predict the emission curves, as we said before. It was not until around the 1900s that a German physicist by the name of Max Planck came along. And what he did was he looked at it mathematically. So in order to explain mathematically the observed emission curve, he introduced a radical idea. He said that, you know what, we know that mathematically we have the wrong prediction, that we predicted this square function, but it doesn't do that. So how do I make it so that I can mathematically describe what that experimental curve is supposed to look like? So you want to come up with a mathematical way of predicting the experimental results. So he really wanted just a mathematical fix. In order for him to do that, he realized that he had to change something very dramatically. He introduced something called the quantum in fixing the math behind this particular problem. And so the idea is that he had to explain how atoms gave up energy in emitting radiation. And basically what he did was he assumed that the radiation was due to the oscillation of charged particles in the atom. So you can imagine inside the atom that these charged particles are moving back and forth and oscillating. That's how they are receiving energy and giving off energy. And classically, if you look at this kind of oscillator, it could vibrate at basically any frequency whatsoever. So what does that mean? Well, imagine this demonstration here. Here I have a little frog that is hung on a nice spring here. If this is considered a classical oscillator, basically the energy is then given in such a way that you stretch the spring a little bit and allow the frog to oscillate back and forth and bounce up and down like this. Now classically, the frog can actually bounce at any frequency that it wants to, as long as I decide what length of spring to give it. So I can change its length uniformly. I can use any length whatsoever and allow the frog to oscillate at any frequency that he chooses to. As long as I can adjust my length of the spring accordingly, I can have the frog oscillate at any frequency that it wishes. So there's no limit as to what kind of frequency the frog can have. In this case, the oscillator can have. That's the classical theory. As it turns out, that didn't work for blackbody radiation. So Planck had to come up with something different. So in countering that, to account for the observed emission curve, Planck concluded that an oscillator can only emit radiation in discrete packets, or what he called a quantum of energy. Now what does that mean? Well, if you compare it in terms of a continuous a selection of all possible energy versus a quantum or only discrete values, we can kind of compare it in the following visual way. Imagine if we can imagine looking at the energy of a ball rolling uphill. In terms of the continuous model, this is what it might look like. Imagine you have a smooth ramp like this, and you would have a ball at the bottom. I can roll this ball to any point along the ramp and have it stop anywhere along it, as long as I have some Velcro that will allow it to stick to it. I can choose any position that the ball will stop at. There's no point that is not allowed. So this is the idea behind continuous energy level, going from the bottom all the way up to the top. I could stop at any point I want to. On the other hand, in the case of the quantized theory, Planck is saying, no. It does not go up a ramp where it's nice and smooth like this, where all possible energies are available. It is actually going up a staircase like this, where if I try to put the ball somewhere in between the first step and the bottom step, it's not going to stay there. It's going to go right back down. There is no way that the ball can basically live, so to speak, between steps. The only way it can go up is to go up to the next step and be able to stabilize itself there, and then go up to the next step, and so on and so forth. So in this case, there's only 3 possible steps that it could be up on aside from the ground. So this is now what we mean by the quantized energy level. And so that was the new idea that he introduced. Now, of course, he had no physical reason as to why this works. He just knew that it worked mathematically. So while it was a mathematical fix to the problem, it really didn't answer why the blackbody radiation problem existed. So that's one big question that a lot of people couldn't answer at the time. So that didn't really give them a full understanding of what the atom was doing inside matter as it interacted in giving up and absorbing radiation. That was the first one. Let's take a look at the second problem that occurred at that same time. So our next topic is now going to be the light emission spectra. In this case, in looking at light emission spectra, what we find is that when you energize a different kind of material, it will give off light. And the light is very interesting. You can actually take a device that will take the light that is given off and spread it out into its spectrum of colors. So the idea is you're spreading it out so you can see all the different energies that are involved in there. It's kind of like the idea of a rainbow using dispersion pattern. So you can use a prism, for example, to split white light into its prism colors, into its rainbow colors. You can do the same thing. Any light coming from any source can now be split up using a prism to see what colors are involved in the light itself. So let's see what these look like. In this case, in the emission spectra of light, we find that different sources of light will basically yield different signatures. First of all, if you look at something like incandescent solids, you take a piece of solid and just heat it up, for example, liquids and dense gases, they will yield something known as a continuous spectrum. So it might look something like this. Imagine I have an incandescent source, like an incandescent light bulb here. And what I'm going to do is I'm going to narrow it down so that I'm going to filter out the light into a very narrow beam using a screen, and then allow that beam of light to hit a prism to have it spread out. So it might look something like this. Now, if I analyze this, it looks like this. This is now a continuous spectrum where we can see all the different colors of the rainbow, going from the red end of the spectrum all the way to the violet end of the spectrum. All the colors are present. So sunlight, for example, is an example of a continuous spectrum where you can see all the colors of the rainbow when it's spread out by the raindrops in the air. So this is one type of spectrum that can actually be produced by a solid, dense gas, or a liquid. On the other hand, there are other kinds of emission that are possible. So when we go back for different sources, another source would be what we call incandescent gases. Now the incandescent gases will now produce a line emission spectrum. In this case, this is what it looks like. Imagine this time I have a tube that is filled with hydrogen gas, I'm going to energize that tube so that it gives off light that will then be filtered out by a slit here that will be spread out this way. Here what we see is something very interesting. We see no colors whatsoever except at certain locations in the form of lines. And for hydrogen, we find that there are 4 specific colors of line that are actually visible, okay, in the spectrum. Very different from the continuous spectrum where all the colors are available. In this case, only 4 colors are available. The question is, well, how come? How is hydrogen different from the light that we get from the sun? Well, people didn't know why there is this difference. Okay? And aside from these two, there's yet another different type of spectrum. So if we go back, what we find is the following. Okay? Another type of spectrum is that when white light, for example, light from incandescent light source or from the sun is passed through a cool gas, a line absorption spectrum is now produced. And notice that, again, the idea of line, but now instead of emission, it is now an absorption spectrum. This is what it might look like. If I have my incandescent light here, my slit here. Now, if I just let the light go through, I would have a continuous spectrum. But this time, I want to put something in between. I want to put some hydrogen gas in between the light source and the prism itself and see what happens. When I do this, I notice something very interesting. Here I have now a spectrum that kind of sort of look like a continuous spectrum, except there are now certain lines missing from the colors. And interestingly enough, when you look at the position of these missing lines, they match up exactly to the 4 lines that we saw were given off when hydrogen was used as an energy source, as a light source. So somehow they must be related. But the question is, well, what happened? Why is this going on? Why are there these differences, in the type of spectra that you would see for different kinds of sources? And interestingly enough, you use different kinds of gases instead of hydrogen gas. If you use helium, neon, krypton, and so on and so forth, each gas gives off a very distinctive combination of lines. And so these lines now can be used as fingerprints to identify a particular element, a particular gas that might be making it in the first place. So the question is, why does this happen? Where is this all going? What is happening in the atoms of hydrogen and so on and so forth, such that when it gets energized, it is giving off light in this very special pattern, these special lines that it's emitting, instead of all the different possible colors. So again, no possible physical explanation that was acceptable at that time. So that's the second problem. Let's take a look at the last problem before we look for the solution. The last problem takes us to our next topic. And this last topic is now going to be the photoelectric effect. And in the photoelectric effect, what is happening is that we're looking at what happens when we shine light onto a piece of metal. And it was noticed that when you shine light on a piece of metal, it had a very special ability to knock electrons loose from that metal. So you can imagine a copper plate, for example. When you shine a certain kind of light on it, you can actually cause a current to flow, pop out. You can now measure the amount of electrons that come out by putting a voltage across there and allowing that to create a current for you. So that was kind of interesting. How does this work? Well, let's take a look. In the case of the photoelectric effect, we find that when ultraviolet light strikes a metal surface, what we find is that electrons are ejected. Now, of course, in order for the electrons to be ejected, it must absorb a certain amount of energy in order to overcome the attraction of the metal. We call this the work function. The way you can kind of use an analogy to understand this is kind of think about what happens when you're on a swing, for example. If you're swinging on a swing, and let's say there's a wall in front of you that's, let's say, 8 feet tall, and what you want to do, you want to be able to swing over and jump over that wall. Well, that means somebody has to push you, so that when you swing high enough, when you can see the top of the wall, then you can kind of fly off and basically fly over the wall. But if you don't swing high enough, you're not going to be able to get over the wall. So something has to give you enough energy to kind of bring you up to a high enough point for you to go over the wall. So what is going to happen there? How are you going to get this energy? When in the case of electrons in the metal, that's the same kind of idea. The electrons are being attracted by the nucleus of the atoms that they came from, and unless you kind of give it energy and tear it away, it's not going to be able to pop out of the metal itself. So somehow it has to get energy from the outside in order for it to come out of the metal. So what's giving it energy? Well, the light's going to be giving it energy. So how is it going to be doing this? Well, let's take a look. So basically, under classical wave theory, it predicts that energy could be gained from any frequency of light with enough exposure time, with enough exposure time. So the idea is, if you look at, again, the swinging of the child on the swing, you can kind of imagine a wave-like structure coming in. So as the person swings forward, you push that person a little bit, swing back. As the person goes right, you push them. So again, the idea of using wave to create resonance. So if you push just right, if you just keep pushing and pushing and pushing, you should be able to get that person to swing high enough to go over the wall eventually. So the idea is this: even if you shine light that has low energy, low frequency, okay, onto the object, as the electrons sit there and get pushed by the wave of the light coming in, if you continue to push on it, you push on it, the electron will continue to absorb energy, and eventually absorb enough energy for it to get kicked out. Okay? Classically, that's what they predict. That's what should happen. Okay? And you can visualize that pretty well. Okay? The problem is that's not what happens. Okay? So what happens in reality? Well, we find that experimentally, we don't see any photoelectric effect, okay, for red, green, or blue light, regardless of intensity and time of exposure. Doesn't matter how bright the lights were. Doesn't matter how long you shine that light onto the piece of metal. Nothing comes off of it. So somehow the electrons were not able to absorb energy, okay, as classically predicted, okay, by the wave theory of light. It just wasn't working for some strange reason. Okay? Again, nobody could explain why. They had no idea as to why, okay, this just wasn't happening. Okay? So in that case, okay, how do you go about explaining it? Well, basically the idea is that if you look at what's actually happening, okay, in reality, with even very weak ultraviolet light, electrons were ejected as soon as the light struck the surface. In other words, there seemed to be very little delay time. There is no need for the electron to sit there and continuously absorb energy from the light itself. So that was kind of interesting as well. Okay? So even with very, very weak ultraviolet light, okay, when it's not very bright, it doesn't matter. Boom, electrons got ejected right away. The difference, of course, is that when you actually intensify the light, what you find is this. Okay? When light of a single frequency was used, changing the intensity, we were making it brighter, only changed the number of electrons emitted, but not the speed of the electron. So here's another interesting thing to consider. Okay? When you shine a particular frequency of light on there, so there's only one frequency, okay, and it is in the ultraviolet range. When you shine the light on there, okay, and electrons started coming out, if you make it brighter, if you intensify it, what seems to happen is that you would kick out more electrons, but every electron that comes out all have the same speed. Somehow all the electrons are picking up the same amount of energy from the light. And that seemed kind of strange. You would think that it would be possible for a particular electron to kind of keep absorbing, and it would actually come up with slightly different values, okay? Especially if the light behaved like a wave. And I think that's what the problem was. Okay? A lot of people they were still thinking in terms of wave, and they could not figure out what was going on in this particular scenario. And it took somebody with a brand new way of looking at things, okay, a brand new approach, to actually come up with a solution to this particular problem. And so let's take a look at, okay, who that person was. This person, of course, was Albert Einstein. Okay? Again, at the early part of the 1900s, he realized that the electrons were reacting to the ultraviolet radiation as if they were a hail of pellets, okay, of radiant energy. And this was a very interesting way of looking at things. Now, of course, a lot of people know Albert Einstein by his other work. A lot of people recall his E is equal to mc squared formula, right? So everybody knows that. Everybody knows him for his special theory and general theory of relativity. Okay, he was very, very well known for that. He was also very well known for his frizzy hair and funky hairdo and so on and so forth. Okay, we even have a poster of him, okay, in our demo area. But the whole idea is that, okay, although he was so famous for knowing everything else that he was known for, okay, this was a major contribution, okay, to the understanding of nature, to the understanding of what atoms really like. So this was actually a very important, okay, discovery that he had. And he had it by looking at, okay, light as if it were packets of energy. He, again, basically what he did was he revived the idea of the quantum by Planck. And so basically, the electrons were absorbing energy from the electromagnetic radiation only in discrete lumps or quanta of energy. Okay? And he called these pellets of light energy photons. So the term photon actually came from Albert Einstein. So when you watch Star Trek, for example, when they talk about the photon torpedo, well, guess what? That's a torpedo made out of light energy. So that's kind of interesting, okay, perhaps down the line in the future. And basically what he did was, okay, he won the Nobel Prize in Physics for this effort. So interestingly enough, Albert Einstein did not win the Nobel Prize for his work on theory of relativity. He did not win it for his E is equal to mc squared equation. He won it for the photoelectric effect. And this just shows you how important this particular problem was at the time, and the solution to this problem really helped to pave the way for our understanding of the atom. And basically what he was doing is relating back to Planck's idea that the oscillators were nothing more than the electrons absorbing and emitting photons within the atom itself. Okay? And this has some very important consequences. Okay? This meant that light had a dual nature. That light not only behaves like waves, but it can also behave like particles. So as the electron is sitting inside of the metal, it is not absorbing the energy as the energy comes by and having it moving up and down and so on and so forth. It was actually being bombarded by particles of light that acted like pellets, acted like BBs, so to speak, and it was like billiard balls coming in and boom, as it collided, it would then carry the energy away through collision processes. So that means that these light particles, these photons, actually not only carry kinetic energy, it also had momentum they can transfer to electrons and so on and so forth. That they were able to transfer completely all of its energy to the electron and give up a particular amount of energy that allowed the electron to not only overcome the work function, to pull away from the nucleus, but also to have enough to have a certain speed as it comes out of the metal itself. And for different kinds of frequencies of ultraviolet radiation, if you have higher values, what will happen is that it will give up the energy, overcome the work function, but it will give it additional energy to make it go faster when it comes out. So you have a greater amount of kinetic energy as it exits if you were to absorb photons of higher energy and so on and so forth. And so light now had this really unique dual phase. It not only behaves like wave, but it can also behave like particles. And this is a very important understanding when we talk about the atom in our next session. So let's go ahead and review some of the things that we've already talked about. So strange as it may seem, what it does is that this new way of looking at light really correctly explains the blackbody radiation curves. It correctly predicts the emission spectra of light, and it will also correctly explain the photoelectric effect. So with this one brand new idea, this introduction of dual nature of light, we can now solve all three of the puzzles that were basically confounding a lot of scientists at the time. And with this single understanding, can kind of pull us into the future of modern physics. And so in review, we see the following. We talked about, for example, classical versus modern physics, pre-1900 and post-1900 physics. We talked about the early models of the atoms as proposed by these four pioneers of these models. We looked at the strange puzzles of classical physics, blackbody radiation, emission spectra, and photoelectric effect. And so for the next time, think about the following. If all atoms are mostly empty space, why is it that when we sit down on a chair that the atoms of our body doesn't just slip right through the atoms of the chair, resulting in a pretty embarrassing moment for us? So the question is, if we are mostly empty space, the chair that we're going to sit down is mostly empty space, the floor that we're standing on mostly empty space, the doors mostly empty, how come we don't just pass through all these things? What makes objects feel solid? What makes it so that when I put my hand down on the counter, my hand doesn't just go right through it? And so think about that. What is it that prevents us from oozing through other material? Because all atoms are mostly empty space, and all different kinds of atoms mostly empty space. Why don't we just kind of move through each other? So think about that until the next time. This is Roger signing off. Think Physics.